We are currently wiring non-deterministic AI agents directly into a highly deterministic, irreversible infrastructure. AI reasoning is stochastic. Stochastic processes are governed by probability distributions, meaning that even with the same inputs, the exact sequence of their outputs remains unpredictable. When an AI formulates a plan, it engages in stochastic intent generation. It drafts hypotheses, hallucinates potential tool uses, and explores multi-step reasoning trees that do not map to static, human-written rules. Infrastructure, however, does not compute in probabilities. Cloud APIs, file systems, and database commands are binary execution events. An action is either executed or it is not. A file is deleted or it remains. Our legacy security models rely on endpoint detection and response, or EDR. EDR functions by passively monitoring the environment and triggering alerts based on known, static signatures of malicious behavior observed after execution has already begun. The left side of this diagram illustrates traditional security. It expects linear, human-paced attacks, relying on a static barrier to intercept a predictable trajectory. The right side reveals the agentic threat. AI adversaries execute recursive loops, encountering a barrier, failing, and instantly routing a new path. Because they can dynamically switch tools and adapt to failures without human latency, they accumulate hostile intent at machine speed. By the time a post-execution monitoring system identifies an anomaly, the agent has already executed its objective. If an adversary operates recursively at machine speed, reactive anomaly detection fails. Infrastructure defense must shift to a pre-execution constitutional boundary, halting intent before it touches a live resource. Enforcing a pre-execution boundary requires a unified interception membrane. Agents cannot be allowed to arbitrarily call APIs. Their intent must be routed through a standardized physical choke point. This schematic shows the governance sensor gateway, separating machine reasoning from the defended environment. The gateway splits responsibility into two layers. The first relies on the Model Context Protocol, or MCP, to standardize tool requests and validate capability tokens. While MCP handles the structured capability negotiation, it does not evaluate the behavioral context of those requests. It requires a secondary system to monitor the actual crossings for anomalies. That secondary layer is the virtual nervous system, labeled here as the virtual network sensor. It acts as an independent observer at the boundary, watching the rate and rhythm of the approved interactions. The VNS introduces harmonic governance. It establishes a baseline for the normal timing and cadence of an agent's tool calls. Deviations from this baseline, like sudden orchestrated bursts or unusual jitter, are treated as first-class authorization signals, triggering immediate throttling. The gateway halts the intent and flags cadence anomalies, but it lacks the analytical depth to approve complex, multi-step actions. To make an authorization ruling, it needs to query a unified, network-wide record of what is actually true. Relying on the ephemeral logs of individual agents or localized telemetry is insufficient. Isolated logs cannot map the dependencies required to detect multi-agent cascading failures across a network. The architecture solves this through an authoritative world state. This acts as a single source of truth, providing a shared decision substrate for every governance node in the fabric. This state is built on an append-only event store. An append-only structure means historical data cannot be modified or deleted, only added to, creating an immutable cryptographic ledger of intents, decisions, and outcomes that can be queried instantly via materialized views. This visual represents the world state graph. Because the data is relational and immutable, the system stops evaluating disconnected alerts and instead reconstructs causal attack chains in real time, mapping initial access to lateral movement. As the graph evolves, persistent objects like hosts and users are continuously updated. Here, the UI entity card shows a degraded trust score and an amber posture for a specific endpoint, dynamically adjusted based on a history of persistent beaconing. To maintain this truth without creating a centralized bottleneck, the state can be replicated across distributed nodes using CRDTs. Conflict-free replicated data types are mathematical structures that allow multiple machines on a network to independently update data and guarantee they will all eventually converge on the exact same state. If the system cannot agree on a single mathematically convergent layer of truth, any governance decision applied to an AI agent is indistinguishable from a guess. With the intent halted at the gateway and the world state providing the context, the architecture must now evaluate the request. Who actually holds the authority to release the action? Relying on a single LLM to validate requests introduces critical vulnerabilities. A single model is highly susceptible to single model bias, prompt injection, and confused deputy attacks, exploits where an attacker tricks a highly privileged AI into executing commands on their behalf. The solution is the multi-agent cognitive arbitration engine. Instead of one validator, it uses a structured core of specialized reasoning agents, distributing the analytical load to eliminate single-point cognitive failures. This diagram outlines triune cognition. It explicitly separates the evaluation process into three distinct operations: belief, action planning, and adversarial dissent. The first node, Metatron, serves as the sovereign belief layer. It reads the shared world state and synthesizes exactly what is happening in the environment. It determines the truth, but it holds no execution authority. The second node, Michael, takes that approved belief and formulates an action doctrine. It maps the agent's cognitive intent into executable candidate actions and calculates the potential blast radius of the request. The final node, Loki, is the adversarial dissenter. Its sole function is to run misuse simulations, deliberately attempting to interpret the exact same action request as a malicious exploit, searching for indirect injections or privilege escalation attempts. This multi-agent arbitration acts as a mathematical constitutional court. An action is only released if it survives adversarial scrutiny from entirely isolated reasoning roles. The gateway membrane, the authoritative world state, and the triune cognitive arbitration do not operate in isolation. They are fused into a strict PDP and PEP architecture. A policy decision point evaluates the rules, while a policy enforcement point physically executes the final ruling. This schematic details the canonical governance chain, plotting the exact flow of intent to prove AI reasoning is decoupled from capability release. Steps 1 through 4 handle request intake, event persistence, and triune reasoning. This half evaluates policy, but cannot touch infrastructure. Step 5 introduces the outbound gate. Actions are locked until tokens are explicitly brokered. Finally, Step 8 is the physical enforcement point, validating the token before terminal execution. By separating these stages, the architecture prevents the most severe failure mode in agentic systems, allowing an AI's internal reasoning, policy permission, and physical execution to silently blur together. The governed execution fabric is not a linear, one-way filter. This final chart illustrates a 6-step closed defensive loop. Every single governed action, whether permitted, modified, delayed, or denied, generates auditable telemetry. This telemetry is insta-refed back into the canonical world state. The evidence of the last execution becomes the context for the next milliseconds decisions. By forcing non-deterministic AI intent through a continuous, deterministic, and adversarial evaluation loop, security transitions from passively monitoring endpoints to engineering an active, self-regulating organism capable of defending infrastructure at machine speed.